Young. I have the lucky job of being the math coordinator in the lower school. I'm also the math resource teacher in the first school. So I work with students from 2 and 9 months all the way up to 10 years old. And then I am part of a pre-K through 12 math department because we want a really cohesive math education for your child. This morning we're going to go over the goals of our math program. You'll see examples of how we design our curriculum. Methods of differentiation. In every class, we have an age span of at least 12 months. And if you think developmentally, if we look at the 1-year-old right there, some children at 9 months are walking, and some at 15 months are walking. So there's a real wide range. How do we handle the wide range of developmental abilities that you would expect to see in every grade? How do we meet every child where they're at? Okay, math goals. We're all about the development of your child's critical reasoning and thinking abilities. And how do you develop critical thinking? How do you provide really meaty problems that children have to wade their way through and do all of these verbs? Just look at them for a second. This is what it takes to develop a mind. So I'm going to give you some examples of the challenges we put out there that your child grapples with. And as they do, they really develop the reasoning skills, and you'll see evidence of that this morning. What's the content we teach in mathematics? The first two, numbers and operation and algebra, I'm going to give you the most examples of this morning, and I'm going to give you a schematic of how we view and teach numbers and operation. Unfortunately, the last three I'm not going to be able to touch on today just because of the vastness of the content. For measurement, do know we teach U.S. customary measurement in math class, so inches to feet to yards, miles, and all of that, ounces to pounds. But we also, of course, teach the metric system, and all of our science, thankfully, is in metric. Data analysis. I see some 3rd and 4th grade parents in the audience, so you have seen homeworks where a child is having to find the mean, the modian, the mean, the mode, and the median of a data set. Growing up, the only average I knew was the mean, where you take all the data inputs, add them together, and divide it by the number of data. And I thought that's what average meant. So your child is learning something different than you might be accustomed to. And I want to give you a couple reasons to pay attention to homework like that. First, it's really important for your own literacy as a consumer. If you read the newspaper now, people always give house prices. They say the median value. They don't say mean. So it's really important that you know that median is the middle. The second reason is you're modeling lifelong learning. But hey, that's interesting to me. I wasn't taught that. Can you explain it to me? Third reason you should pay attention. Pops up on the SATs. Geometry is a huge topic. We could spend an hour on that. What I want you to know is that we very carefully develop your child's spatial reasoning capacities. But in addition to the content, we really want to develop your child's capacity to think like a mathematician. And there are some habits of mind, some ways of thinking and attitudes about math that are very important to cultivate in your children. I'm going to give you examples for the most part of the top two. Children are natural pattern finders, pattern seekers. We put out Fibonacci series to our second graders the first week of school. I'll be darned if they didn't crack the code. It just took them 2 days. They looked at it. It was really interesting. So that is natural for them to break apart things by looking for regularities, looking for patterns. The way I'm going to show you models is I'm going to let you see what your own model for thinking is, and then you'll see how we develop it in children. In terms of organizing and reorganizing information, this really comes into play next month in 4th grade. Our 4th graders take a hundreds chart and they cross out any number that has more than 2 factors. So they would cross out 6 because its factors are 1, 2, 3, and 6, the numbers that you can divide a number evenly by. What's left, they've highlighted in yellow, and those are prime numbers. So they look at the ones in yellow, and we say, you know what? We know a good math problem, can take a class or 2 to solve. But here's a math problem that's taken hundreds of years to solve. Nobody's been able to find a predictable pattern amongst prime numbers. Because you want to be able to predict the next prime number, and you can't. We haven't been able to yet. And 4th graders are the same. It's impossible. There has to be a pattern. And they spend about 2 months thinking about this. And the reason I know they're constantly churning it over is they have mass sharings that they do every week. And lo and behold, every math sharing, well, here's what I did so far, and I found a pattern from here to here. But it didn't work, so then I looked this way, and they continually go. Now, mathematicians still work on this, right? This is a problem that is really comes down to how can you reorganize the data to find a pattern. So, all right, so let's jump into a problem. This is a problem our fourth graders worked on. So here's the way the puzzle works. You start with 7 red counters. You need to turn the counters over so that their yellow sides are showing. Here are the rules. You can turn 3 counters over at a time. As a matter of fact, you must turn 3 each time. You can choose any 3. You don't have to go consecutive. You don't have to turn the first 3. You can go random. Then your next move, you have to turn 3 more counters over. You can choose to turn something back to red. So if you turned it over and became yellow, you can flip it back to red on a subsequent move. Every move, you must turn 3 counters. Does that make sense? Mm-hmm. Give it a try.
And what's the goal? What's the
goal? To turn all of them over into yellow in the fewest possible moves.
Great.
Now, just so you know a little bit about our fourth graders, they absolutely dove into this problem, and some solved it very quickly. So I'll show you what we did with those students. Some got frustrated with it, so we said put it away, and they took it out the next day and did another 10 minutes. Got frustrated, put it away, and everybody came up with a solution, and then we started to analyze the solutions for efficiencies. So I'm going to stop you. I would never stop our students from working on a project. I'm going to move you along and show you one solution. This young man looked at it, and this was his first try. So I gave him a recording sheet, and I said, record what you did, because I wanted to see if he could repeat his steps, right? So he started all red, so he's colored them red. And then in his next move, he turned 1, 2, 3 over. And then in his next move, he turned 1, 2, 3 over. And by doing that, he gave himself 3 reds. So he solved the puzzle in 3 moves, which is rather elegant, isn't it? Now, if I hit this, it should take us to the internet. Go back to red. Do we have any computer coders in the room?
Long time ago.
Right. Okay. The reason I ask is when you can take a problem and really solve it simply and elegantly, it's like writing a piece of code that's not repetitive. You're bringing it down to its basics. So go ahead and flip your first, your second, and your last. And now we're going to flip your third, your fourth, and let's flip the last again. And lo and behold, on our third move, do you see the 3 we have left? So we can flip these over. So if a student is able to do it in 3 moves, the first thing I do is change the parameters. So I'm going to say, okay, can you do it now flipping 5 at a time? Because I want to find out, did he have beginner's luck? Or does he know what he's doing? Has he created a structure of the problem in his mind? So 5, 1, 2, 3, 4, 5. Let's see what happens. So I have 2 left. That gives me 5 red. So then, if he's able to do that and again solve it in 3 moves, I know he has internalized the structure of the problem, and again I can up the ante. So now for this student, I would take the counters away and I would bring him to an iPad, and we would load the site and I'd bring the problem to scale. So we use technology as one of our extension tools when it makes sense, right? To work with 19 counters would be cumbersome. To work with 7 is actually delightful. And it's really important that they have the practice of flipping them. So let's look at what, again, that student was doing. Let's look at this line right here. He's moved his 3 counters, so he has 4 red. So in his mind, he's going, I've got 4 red, gotta get it down so that I only have 3 red. So I'm going to flip 2 red. That's going to bring me down to 2, and then I'm going to flip 1 yellow. Do you see what he's doing? So this here is the 3 counters that he moved. He brought 2 from red to yellow, 1 from yellow to red. So his construct underneath this, he's seeing it as addition and subtraction. The more I talked to him, I realized he was seeing positive and negative numbers. So look ahead to middle school. These are the exact counters we use when students start their formal study of integers, but you can see we started informally here because we're building a pre-K through 12 program, and we want to make sure the education is continuous and that the foundation is there. So by the time they get to the formal studies of integers, they have an understanding in their gut of what it means. So here's another pattern that our fourth graders will start actually next week. What I love about this is it's just a review of multiplication facts. So let's say I was doing my times sevens, because sevens are the hardest for our third graders to remember, so it's what we review in fourth grade. So 0 times 7 is 0, 7 times 3, and 70. I'm always going to stop when I get down to the 0. So we go over here, and what I'm going to do is just take the ones place digit and connect all of those digits. So 0 to 7, right? 0 to 7. Next I'm going to go to 63, back to 70, and I've made a 10-point star. Interesting. All right, well, let's try times 3. 2, 15 ends in a 5, 18, 21, 24. Hey! It's the exact same thing. Coincidence? The kids wonder. So I said, all right, let's do another one. Let's try times 6. First question I asked your kids, is it going to be 10 points again? Without hesitation, they said, can't be. It's even. You can't get an odd product with an even fact. How do they know this? They've been looking at patterns for a long time and noticing, oh, odd times odd is always odd, but even times even, and even times odd is always even. So a 6 point, right? 12, 18, 24, 35 point. Is there going to be one that is the converse of this? The exact same points, but in the opposite direction? What do you think? Thumbs up, yes? No? Not sure. The same way I would gauge with your students. Yes? No? Not sure. And the thumbs are private. Okay. So I see a lot of yeses. Lo and behold, you're right. So here's what the kids end up with. They find that the multiples of 4 and 6 share a 5-point star. 3 and 7, 10 points. 2 and 8 are a pentagon, and 1 and 9 create a decagon. And then by the time we pause, there's a huge buzz in the classroom because they go, look, that makes 10, that makes 10, that makes 10, that makes 10. These go back to their tens partners that they've learned so well in first grade. And they go, why? What does this have to do with the base 10 number system? It's all part of putting the structure together. So what is the schema for our teaching numbers and operation? We literally view it like building a house where you want a foundation that is as deep as possible. And in your foundation, in your basements, is your heating, your electrical, and your plumbing. And those systems run throughout the house, do they not? The way these systems run throughout the house. Again, critical reasoning is always, and critical thinking is always our end goal. But this is where we start with the building of the foundation. So today you're going to see me talk about place value, and one of our number fact strategies, the tens partners. Number sense. Best way to understand number sense is a child who understands the meaning of numbers, their magnitude, number relations, and how operations affect numbers. Let me give you a concrete example. If I was adding 3,996 to 4,512. Let me say, okay, add that. What would you do?
4,000 plus that, and then subtract 4.
Perfect. Anybody else? What else would you do? Because I saw some of you going like this. And in your mind, you're lining them up and trying to do your column addition. That is your model for thinking. Because that's what was presented to you early on, and that you made a visual imprint, and that's the way you think about numbers. That algorithm, which is a procedure, a step-by-step procedure for multi-digit computation, we teach so the children are fluent in it, but we don't teach it as the first strategy. They have to earn it. We don't give them the shortcut until we know that foundation is really deep. So what she did is she goes, this is really close to 4,000, is it not? As a matter of fact, it's just 4 off. So she added 4,000 to here. She got 8,500. She also knew she needed to subtract 4. So that's computation with number sense. You look at the numbers involved and go, what's the most reasonable way for me to compute this? You don't automatically apply an algorithm, though sometimes the algorithm is the most efficient way. So, this is supposed to be up here. So here's a child who's putting together the place value schema. So you've got 3 numbers and a comma. This denotes a numeric period. Your ones are your units, your thousands, your millions, your billions, trillions, and so forth. And she sees a repetitive pattern in there of ones, tens, hundreds, ones, tens, hundreds. And that helps her anytime I say, so where is your 4? Oh, it's in the 100 millionth place. Where is your 8? Oh, it's in the 1000th place. The repetition really helps kids consolidate place value. But then when you get to decimals, the pattern ends. It's no longer ones, tens, hundreds. They want this to be the ones, but it isn't, right? It's the tenths, the hundredths, and then the thousandths. 5 consonants together. They're like, are you serious? So once we get to decimals, and they can no longer rely on a repetitive pattern, they have to think more deeply about the relationship between the ones and the tens. And as you know, you saw in Back to School Net, we use base 10 blocks in 2nd and 3rd grade a lot to build some of the number concepts. And so we asked, well, what do you know about the ones? Well, 10 ones make a 10. And they know 10 tens make 100. And they know 10 hundreds make 1,000. And they know conversely, we can take our thousands and we can break it down into 10 hundreds. We can take our hundreds, break it down. We can take a 10 and break it down into 10 ones. And then they know that decimal, the tenth, is 1/10 of a 1. They know it's 10 times smaller. And each time we're getting 10 times smaller. So they can apply the converse. 10 of these bring you to the next place value. Multiply it times 10, you get to the next place value. And now all of a sudden, the structure, the mathematical underpinnings of the place value system become apparent, and they say, oh, it's a multiplicative system. It's based on powers of 10. And that's the deep place value understanding we want our 4th graders to have by the end of their lower school experience. So can they use it? So this child knows that our number system uses just 9 digits, 1 through 9, and the symbol 0 to make any number. So how is he applying it? Number 1, only one of these answers is possible. Decide which is correct, circle it, explain your reason. I said the highest sum is 649, and the lowest is 505. So it can't be 503 or 429, it must be 613. Child doing. He's replacing the hidden digits with the lowest possible digit. And going, if I add those together, my highest sum is 505. I mean, my lowest sum. If I replace the hidden digit with a 9, my highest possible sum, am I doing this right? 18, 19, 6. And so in his mind, or on paper, he's made a mental number line, and you know the answer has to be in between those 2 points. And that's how we've eliminated these 2. Here are tens partners. These are our 1st graders. They are coming up with all the number combinations that make 10 with 2 add-ins. Here they get very sophisticated, saying this column of add-ins is increasing by 1, while this column of add-ins is decreasing. They also see the commutative property, 2 plus 8 is the same thing as 8 plus 2. This is the only time where we use a phrase called turnaround facts as opposed to commutative property. But for the rest of their math vocabulary is always very precise. Here she's using monsters to show 6 plus 4 to her partner, who's then recording it, and with her fingers and her puppet she'll make all of the tens partners. Here she's making flashcards based on a model like this that you guys have seen. If you've been in the 1st school, you're very familiar with her 10 frames. They're doing the same there with 10 frames on a train, creating all of the possible 10 partners and then recording the partners there. Tens partners become a way for our children to mentally compute. So a 2nd grader who sees 38 plus 5 is going to split that 5 into 2 plus 3 so that they can link that 8 and 2 to immediately make a 10. They've got 40, so my answer is 43. All right, this is the second grader in their handwriting doing what I just showed you, but it's their mental math, what they do in their head. We don't actually force them to record their thinking all the time and say you have to write it out. Every once in a while we say illustrate what's going on in your brain so we can, so you can share the quality of your mental thinking with others. So here she's got her 73, she's broken 6 down into 3 plus 3. She really could, it would be more efficient to move it to this 3, but she wants a nice big smiley face because this is really fun to do. Over here, she's doing the same thing with her subtraction, breaking it down so she can make an easy 40. When she's subtracting 3, she knows the tens partner to 3 is 7. So the subtraction is instantaneous. Okay, multi-digit addition. This is a second grader. Let me start over here with the algorithm you know, and that all of our second graders learn, all of our third graders become completely proficient in, and our fourth graders are fluent. When I did this super fast, and moved with that lights in my eyes, did you see how I digitized? I said 6 and 6 is 12. So I'm putting my 2 here and my 1 up there. But is this a 1? Looks like a 1. It's not in 1's place. And I said 12, so maybe it's a 10. It's in the 100 place. What is it? Do you see by digitizing, I've lost my sense of place value? Now, your child has to be able to explain to me that 1 means 100. And it came from the fact that this is 60 plus 60 is 120. So that 2 means 20 and that 1 means 100. How do they get that sense? Again, they have to earn it. So we start by charting their mental math. We start with all of our problems horizontal. Why? 48 plus 37. Why am I starting that horizontal? Well, your child reads left to right. And when you read left to right, you see the tens place digit first, or in this case, the 100th place digit, the digit of greatest value first, which helps you with your estimation skills, by the way. When you have to estimate a sum, you don't start with the ones place. You start with the largest place value, correct? So they're used to reading, so they're starting from the left. But when I say the word 48, what do you hear first? 48. You hear the big number. So it's natural for them to start to the left. We don't teach them start from the left. They naturally do that, and it actually helps build their number sense. So we don't discourage it, because it's a really good thing. So they say 40 and 30 is 70, 8 and 7 is 15. Now I've got 70 plus 10 more gives me 80 and 5, 85. You see, you know what? It's kind of hard for me to see. Could you put it vertical? So we have them recorded vertically. 40 and 30 is 70, 8 and 7 is 15, and then they join those parts. Because I want them to be able to work in a vertical column, so eventually this transition's pretty easy. Because when you have a lot of numbers, this algorithm is beautiful. Right? By third grade, they are proficient at quickly estimating, and estimation is a skill your children will completely need in this workplace. Most of their addition, subtraction, multiplication, division is going to be on a calculator or a computer. They just need to quickly go, did somebody input a digit wrong, or did I forget a digit? And how are they going to know that? By being able to ballpark estimate. So we always have them estimate, and then do their actual, and of course check with inverse operations. Here are our fourth graders. So they leave fourth grade fluent in multi-digit multiplication and long division. They can interpret remainders as fractions, decimals, or just leftovers. This long division algorithm serves them well. Here's an upper schooler who is dividing a polynomial by a binomial, and she is just using the long division steps. So we really do want them to understand the algorithms and be able to use them. We think they're important. We just don't teach them first, not until they're ready. We make sure they earn it by understanding the place value components. Developing the concept of difference. We start in first grade because sometimes if a child learns that subtraction is takeaway, because that's what grandma showed them, because it's easy to do when they're 4 or 5. That first definition of subtraction can become their only definition, and we work really hard to make sure that they know subtraction is also finding the difference, which is 95% of the subtraction that you do as an adult. It is comparison. It's not really taking away. So here we've got 2 students, Parker and Joey. They're up at our number line, and they find one person's head goes up to the 49, Joey goes up to the 43. They count up to find the difference, and the difference in their heights on this number line is 3 units. We then move into physical items. So a child has built a compute a tower of 14 and 9, and he has rung the difference and counted up to find the difference is 5, and learned to translate it into a subtraction number model or equation. Knowing when to use takeaway and knowing when to find the difference takes cognitive flexibility, and it's something we have our first graders do right away. So let's say I'm rolling the dice and we get a 6 and a 1. My sum is 7 and my difference is 5. I'm just going to count that 1. But if my dice roll is a 6 and a 5, my sum is 5, do I expect that child to count back from 6, count back 5? No. Here they're going to find the difference and count up from 5 to 6 and know the difference is 1. That switching of gears and selecting a strategy is one of the cognitive demands that we put on our first graders. So how do we differentiate this game? Because in every first grade class, there are going to be numerous computational abilities. And we do it through the dice. And I have dice. So if a child is ready for numbers going up to 10, 12, 20, and as Rhett saw, we've got our 30-sided dice that we're going to use in a minute, so I'll give that to you. I can have them roll 2-digit numbers, 33, 333 with our place value dice. I can go all the way up to the 100,000s. I can take the child into decimals or fractions. So in the classroom where everybody's playing, see if it goes backwards, this game, I can have multiple levels going on at once. And we found when you switch one person's dice, all that matters is that everybody gets a chance to use more than one dice. They want to work with numbers at their edge. They don't necessarily want to work with those numbers over there. They know what feels the right stretch for them. So a second grader came to me and said, you know that game we play where we find the sum and the difference? I said, yeah. He goes, well, what if you totaled them? I said, well, what if we totaled them? So turn your sheet over. And we're going to do 3 rounds. And I'm not going to record up here what the rolls of the dice are. I'm going to ask you to record them and then hide it from me so I don't see the front row. So, Rhett, go ahead and roll our dice. Tell us what we got. So we have a 29, and the next one is, give us our next number.
12.
All right, so you are recording 29. Ooh, it's going to stretch my brain. And 12. Don't let me see your papers. So we were playing this. And then a student came up and said, I'm noticing something. I said, you know what? So am I. What we noticed is with this piece of information, these 3 pieces of information on any given line, we could work backwards and tell you what you had rolled. So I'm going to try to figure out what you rolled. I can't believe I'm doing it with this 30 dice. I can't tell you the order in which you rolled them, but I can tell you what the 2 numbers are. So over here, you must have rolled a 29. And if one of them is 29, then the other has to be 12. Is that correct?
Yep.
Yes. What am I doing?
You're dividing 2 at the end. Algebra.
Why? Algebra. So let's write it this way. If my roll is an A or a B, A and a B, here I'm adding them, here I'm subtracting them, here I'm combining them. So let's combine them. A plus A is 2A. Plus B minus B is 0. So our second graders are pulling out that pattern, and they can see that they doubled the number. Now, I'm not showing it to them algebraically. They're thinking what happens when you join the sum and difference of numbers. So let's go into algebra. So here we've got first graders. They had the marvelous math machine. This is a function machine. The rule that they have put in, you can't see it, is +5. She's put in the card 12, and out! The mathematician has copied a 17 that she has quickly written down there because she's figured it out. So they're learning how a function works. She loved it so much she went home and made it with her babysitter and brought it back in so that she could practice. We quickly transitioned to the board where we make an in-out chart. Again, the rule is -3, so in goes 12, out comes 9. Very similar to what they're going to be doing in middle school. This is a 4th grade problem. Same shapes are the same numbers. Different shapes are different numbers. And the end of each row is the sum, and each column is the sum. So where do we start? The kids go, well, let's look at row number 2. There's just a triangle there. And we know 12 plus something is 18, so that something must be 6. Agree? Where do you go next? Let's go to column 2. We've got 2 circles. Those circles plus 5 must be 9, so the 2 circles together have to be 4, so each circle has to be 2. Same shape is the same number, so that's 2. If that's 4, 4 minus 12 is 8, so this has to be 8. What have the students just done? They've learned how to isolate variables. They've in fact invented it. Next puzzle. Oh, they can't isolate those variables. So we said, well, what's different about them? Well, look, we've got an extra circle on that top one. Well, what's the same? Well, they both have a circle, a square plus circle. Oh, they both have a square plus circle. So this together has to be 11. I know that because that's what they say. If that's 11, this has to be 5. And if that's a 5, this has to be 6. So the 4th graders have just invented substituting one equation inside another.
Which grade is it?
4th grade. So then we get to a puzzle like this. Now we've got 3 variables. I put this one on your paper so you have a minute to look at it. We've got spheres, cubes, and cylinders. But let's pay attention to the question. Which block, singular, will balance C? There is one block we need to put over here to balance that final pan balance. So let's just work our way methodically through it the way your 4th grader would. They go, well, I see 5 spheres here and a cube. I see cylinder and a cube. Boy, it'd be a lot easier if I took those cubes off. Because I can lift those cubes off and it's still going to balance, correct? Because the cubes weigh the same amount. So now I know 1 cylinder equals 5 spheres. I'm going to try to put this little decoration in my sphere so we don't accidentally think it's a 0. We go over here. Cylinder, sphere, cube. Cylinder, cylinder. Well, let's take a cylinder off of each side. That's going to simplify it, won't it? Okay, so now I've got a sphere and a cube and a cylinder. Wait a minute. I know that cylinder is worth 5 spheres. And over here, I've got 1 sphere plus a cube. So now I know that cube must equal 4 spheres. Agree? So let's see. 3 spheres and a cylinder equal a cube. Let's put it all in spheres. 3 spheres plus a cylinder is 5 spheres, so that's going to be 8 spheres, equals a cube. And we know a cube is 4 spheres, so I have to add, another 4 spheres. So I'm going to put a cube over here to balance it. So which block will balance C? A singular cube. Once I do that, now I can extend and give numeric relations to each of the objects and figure it out. Figure out the next set of problems. So our 4th graders, without us teaching them, have invented 4 of the primary steps that they're going to be using in their middle school algebra. So let's do just 2 seconds of middle school algebra. Let's just remember how to solve this. Remember how you'd say x times x squared, and x times 9 plus 3. What math is this based on? It's based on what they learned in 3rd grade, the distributive property of multiplication. So here's the 4th grader, right before I'm about to work on the multiplication algorithm with her, teaching her the shortcut. I need to make sure the foundation's there. So I said 7 times 36, so show me all the ways you know to solve it. First thing she does is apply the distributive property. She breaks her 36 down into 30 and 6 place value components, does her multiplication. Here, she's doing this exact same thing vertically. We call it partial products. It's 1 step before the algorithm. 7 times 6 is 42. She writes the entire number out. 7 times 30, not 7 times 3, 7 times 30 is 210. Okay. Here, she tells the story. She goes, well, let's just think of that hall in 4th grade. It's really muddy right now. We've had a lot of rain. We need to have a big long mat. It's going to be 7 feet wide and 36 feet long. And let me tell you its area. So she knows multiplication can be used to find area. She breaks again her 36 down into 2 easy pieces to multiply, adds them together to get her product. She's ready for the shortcut. Do you see how the distributive property is apparent in all of this multiplication, and it's exactly what's needed here? So let's do this. We have to factor, again, this would be a 7th or 8th grader. We have to factor this. So I'm going to put my parentheses out. We know we're going to get an 8 here, an x here and an x here. To do this factoring, I need to be fluent in addition, subtraction, and multiplication, correct? How do we build that fluency? In the lower school years. So if you look at this, 4th graders were asked to circle the multiples of 2. We did that. Star the multiples of 3. So you see your stars, 3, 6, 9, etc. Dot the multiples of 4. X the multiples of 6. Okay, done that. Why? You will be lifting your right arm on a multiple of 2. Lifting your left arm on a multiple of 3. Right leg if you want to. I'll have you do 2s and 4s. You can start with the first 2. Stand up. Let me show you how this works. Okay. We're going to practice. We're just going to go to 12, and we're just going to do, I'm going to do it backwards. So that when we hit a multiple of 2, you'll raise your right hand. When you get a multiple of 3, you're going to raise your left hand. So I'm going to mirror you. Does that make sense? Okay, so we're just going to do 12 as a warm-up. So 1, 2, 3, 4, 5, 6, right? It's both a multiple of 2 and 3. 7, 8, 9, 10, 11, 12. Okay. So as I saw our 4th graders go off to music and French, they travel around, I would see them working it out in their heads and rehearsing, and one student ran back into the room and said, I got it. I know why we have 60 minutes in an hour. Because you know how we're jumping? 12 and 24, 36, 48, 60, they're all multiples of 12. So I started to work on 60. 60 has the most factors of any number under 100. So we stopped there. We go, is that right? And we investigated all the factors of numbers under 100, and lo and behold, she was right. 60 has the most. So we said, well, why does this have anything to do with time? Well, you can divide it up so many different ways. It's really useful. And she's exactly right. This is one of the remnants of the Babylonian place value system that we talked about earlier in our time. So when you see these number games and a child going home doing this, that type of number play is to build the fluency and flexibility that we want them to have as a prerequisite for their work in the middle and upper school. So we're going to end with this. Another habit of mind of a mathematician is that they observe natural phenomena. So here's the problem. Mr. Branscombe, a 4th grade teacher, has 75 chocolate rabbits to share equally amongst 22 friends. How many whole rabbits will each friend receive? This is a trick question. Mr. Branscombe does not share chocolate. To which she says, too true. And then she has an arrow, and on the back she shows the long division and her answer. Mr. Branscombe's friends get 3 whole rabbits. So that is our presentation. Thanks.